Hello everyone, my name is Franco Pucci. I'm the technical consultant for the STS Association. Welcome to Training Video Series 2, where we will explore the companion specifications. I hope you find these videos helpful. In this video, we will look at the STS101-2 companion specification. Please refer to the relevant document for detailed descriptions. And the document in question is the STS101-2 physical layer protocol for a two-way virtual token carrier for remote connection over DLMS COSEM. This document specifies a new token carrier that allows for the transportation of STS tokens over DLMS COSEM channels, while simultaneously supporting the existing token carriers such as defined in IEC 62055-51 and IEC 62055-52. DLMS COSEM is a widely accepted protocol standard being used by smart metering devices all over the world, enabling bidirectional communication between a head-end system, client, and an end device server. The token carrier itself is not specified in this document, only the protocol. The STS message is an ASN1 message encoded using the AXDR encoding rules and is contained within the DLMS COSEM message block as a variable length octet string. If we look at the reference documents used, then we can see that there's quite a number, the first being 62056-5-3, edition 3, which is Electricity Metering Data Exchange, or the DLMS COSEM Suite, part 5.3, application layer. Then you have 62056-6-2, which is the COSEM interface class. You have 62056-6-1, which is the OBIS codes, and 61334-6, which is the AXDR encoding rule. In addition to that, we have the RTUT X690, which is the ASN1 specification of basic notation. You have the document we're discussing today, which is the STS101-2. And then you have, of course, the ever-present IEC 62055-41, which is essentially the STS standard. The document we're discussing is complementary to the application layer protocols specified in IEC 62055-41 and should be used in conjunction with that standard. There is a path from the POS to the meter, and there is a return path from the meter to the point of sale to convey the result of processing. The main objective is to integrate the transfer of data to and from an STS compliant meter using the existing DLMS COSEM protocol, which is today widely used in the smart metering market. The protocol specified in this document makes use of the DLMS COSEM protocol and specifies a data format for inclusion of an STS payload within this DLMS COSEM protocol. In other words, a method of exchanging data to and from the meter, STS meter, using an existing channel, which is the DLMS COSEM channel. In practice, the token is entered into the payment meter by means of, for example, a keypad, a mobile handheld unit that connects to the payment meter by way of a direct local connection, or a remote management system by means of a suitable interposing modem device linked over any appropriate communication medium. The connection itself is not within the scope of this specification. However, the format for the data in such extended remote connection is specifically covered in the standard. Some of the acronyms we were using in this video and subsequent videos are ASN1, or Abstract Syntax Notation 1, AXDR, BER, which is Basic Encoding Rules of ASN1, COSEM, DLMS, TCT, which you should be familiar with, which is a token carrier type, token data type, TDT, TID, which is a token identifier, which should also be familiar with, and VTC, which is a virtual token carrier. Let's have a look at the DLMS domain entities. On the one end, you have an HES application process, in other words, a head-end system. And on the other end, you have the meter application process. The DLMS system essentially consists of a client application layer, a server application layer, a token gateway, a COSEM account, COSEM credit, and COSEM charge. And these are specified in the IEC 62056-5-3 and -6-2. On the other side, on the STS side, we have the IEC 62055-41 document that essentially specifies the vending application layer, the meter physical layer, the meter application layer, and the STS credit. What we want to do is introduce an STS token gateway, and that allows then the vending app to send tokens via the STS 101-2 document or token carrier through to the server application layer, through the token gateway, and to the meter application layer. Okay, so what we will be focusing on is the STS token gateway, the purple bit in here. The token gateway itself receives the data in an ASN1 encoded request message. It extracts the STS tokens from the request message and submits them in order to the STS application layer, stopping if a token is rejected. It formats the results from the STS application layer into an ASN1 encoded data value and then returns the token status structure, which includes this token data value. The token carrier itself is a message in ASN1 format in a compliance with RTUT X690, encoded with an AXDR encoding rule as per the IEC 61334-6 document. The point of sale sends the token or tokens to the meter by encoding them onto the token carrier as described in STS 101-2. Then invoking the enter method on the STS token gateway. There are several possibilities to get data to and from the meter. One is the enter method, one is the get request. Let's have a look at each one of these. So, once again, on the left-hand side you have the head-end system, and on the right-hand side you have a meter. And in between them you have an application layer for vending, you have an STS token carrier, you have a DLMS server, an STS token gateway under DLMS, and the meter application layer itself right through to the meter. So what happens? When you send a token, the head-end system generates this token. The token data, which consists of 66 bits, is sent through to the token carrier along with any service parameters that may be required. An action request is generated, which is then sent through from the STS token carrier essentially through to the DLMS server. The DLMS server generates an enter method. There could be a token lockout defined sometime in the future just to stop people, hackers really, sending arbitrary tokens until they get one right. But this has not yet been defined. The token data is then sent through to the meter application layer, and at this point you could get an authentication or validation result or both generated if it is an incorrect token and token is not recognized by the meter application layer. If it is, it goes through to the meter, and then the token along with the authentication and validation results go through to the meter processes it, generates a token result, executes the token itself, in other words, increases credit or changes power limit or does a key change or whatever it needs to do, sends a token result back through to the DLMS server. The DLMS server generates an action response, and essentially the token status then goes back to the head-end system. The head-end system sends through a token request and receives back a token status. In other words, did your request pass or fail? On a GET request passed to meter, you have the STS token carrier, DLMS server, and STS token gateway. The GET token for the most recently processed token is generated, This generates a GET request with an attribute attached to it. That goes through to the STS token gateway. Once again, there could be a token lockout at some point in the future. An action result is generated by the emitter through the token gateway back to the DLMS server. The GET response is then generated and sent back as a token description. The token description itself contains the STS token class, the STS token subclass, the token ID, and the token amount, and they're all in octet strings. In the next video, we're going to look at a GET request, a GET response, an action request, an action response, message definition in ASN.1 format, the response message, and a worked example. This brings us to the end of this part of the video series. I hope you found this video helpful, and I hope to see you for the rest of the video series. Goodbye and see you again soon.